Hello everyone, in this video we will cover the section 1.4. In this section we will see the matrix equation which is written mathematically a times x is equal to b. So if A is an m by n matrix, namely we have m rows and n columns with the columns a1, a2, blah blah, an, okay, and if x is in Rn, which means that we have n components for the vector x, then the product of a and x, namely this one, okay, a product x, namely we have a matrix here which is m by n. Let's write again. A has the size m by n and x has n components like x1, x2, blah blah, xn, you see. Therefore it is a matrix m by n, m by 1, okay, m by 1. We have n rows, n rows. In the first row we have the only number which is x1, and we have just a single column, okay, for the vector x. We use the matrix notation to state a vector in this course, you know. Therefore the product of a and x is the linear combination of the columns of the matrix A using the corresponding entries in x as weights. In other words, mathematically we see that if you write the columns of the matrix A, by the way, as I said, A is m by n matrix, which means we have m rows and n columns, namely A1 has m entries, okay, m columns, m components like A11, A21, blah blah, AM1, AM1. Okay, we have m rows. You see, first we write the number of row, and then we write the second number is corresponding to the number of column. Okay, since we are in the first column for A1, so we write A11, A21, A31, A41, AM1. So each column has m entries like this one. But compactly we write the matrix A with its columns like A1, A2, blah blah, an, to see easily the product of the definition of the product of a matrix and a vector. And as I said, we have the size is m by n, and the vector has the size n by 1, okay. Namely, the number of columns you see is equal to the number of components of the vector. You see, we have n columns here, n columns, and we have n components, n components. Namely, to define the product written here, so we have to have n columns for the matrix, and we have to have n components for the vector. And then the definition is that just we write the linear combination of the vectors a1, a2, blah blah, an by considering the weights as the components of the vector, namely x1 times a1, x1 times a1. x1 is a number like c1. If you write the components as c1, c2, blah blah, cn, you can write c1 a1, c2 a2, blah blah, cn an, okay, c1 a1, c2 a2, blah blah, cn an. The notation is not important for stating the components of the vector. So here we write x1, x2, blah blah, xn for the weights of the linear combination written here. Therefore, to find the product of a matrix and a vector such that the number of columns is equal to the number of components of the vector, so we write the linear combination of the columns of the matrix A by considering the weights as the components of the vector x. So note that A times x is defined only if the number of columns of A equals the number of entries in x, as I say. For example, for v1, v2, v3 in Rm, which means that we have m components for them, write the linear combination 3 times v1 minus 5 times v2 plus 7 times v3 as a matrix times a vector, a matrix times a vector. So place the vectors into the columns of a matrix A and place the weights written here into a vector x. In other words, this linear combination can be written in this form by using the definition here. Okay, we have the right side of the equality and using the given information on the right hand side, so we can obtain the left hand side. So the columns of the matrix will be the vectors v1, v2, v3, you see, and the entries in x will be the weights of the linear combination, which are 3, minus 5 and 7. 3, minus 5 and 7. Okay, another example. Let's give another example. Okay. So we have a matrix A whose entries are 1, 0, 1, 0, 2, minus 5, minus 1, minus 1, 3. So we have 2 rows here and 3 columns, so the size is 2 by 3. And the vector x has the components 4, 3, 7. So we have 3 rows, 3 entries and 1 column if you consider it as a matrix. Okay, so we say that x is in R cube. Okay, it is a vector in 3-dimensional space. And when we consider the columns of the matrix A, let's say this is A1, this is A2, and this one is said to be A3. Okay, so we have 2 entries for each one, which means that they are vectors in R square, which means that we are in 2-dimensional space. Okay, we are in 2-dimensional space for the columns of the matrix A. So let's find the product of the matrix A, which is 3 by 2, 2 by 3, sorry, and the vector x is 3 by 1. So you see that the number of columns is equal to the number of entries in x. So we can apply the product according to the definition. It is just the columns of the matrix A times the entries of x in x. So we write, so if you consider generally, it has the components x1, x2, x3. Therefore we write x1 times a1 plus x2 times a2 plus x3 times a3. So we have from here 4 times a1, namely 1, 0, 1, 0, plus 3 times 2 minus 5 plus 7 times minus 1 3 minus 1 3, and from here it is equal to using the scalar multiplication for vectors, you know, from calculus 2. So we have 4 0 plus 6 minus 15 plus minus 7 21, and from here we obtain using the vector addition, if you remember from calculus 2. So we have 3 for the first component, for the second component we have 6. So we obtain actually 2 by 1 vector, okay, if we consider it as a matrix. So the result, you see, this is equal to a vector, let's say B, which has the size 2 by 1, namely we cancel the numbers, the common number 3, and we obtain 2 by 1 vector, 2 by 1 vector whose components are 3 and 6. Okay, therefore the matrix equation A times X is equal to B is actually corresponding to x1 times a1 plus x2 times a2 plus x3 times a3 is equal to b. As you can see, this is equal to, this one is equal to b. Okay, b. Therefore this equality corresponds to this vector equation. It is called the matrix equation, and this one is called vector equation. A1, A2 and A3 are vectors, and B is a vector, and x1, x2, x3 are scalars, weights. Okay, the left hand side is the linear combination of the vectors A1, A2 and A3. Okay, so now write the system of linear equations as a vector equation involving a linear combination of vectors. For example, namely we have a system of linear equations as a vector equation involving a linear combination of vectors. So we have a system here, a simple system. We have two linear equations with including three variables, you see, x1, x2, x3. So it is equivalent to x1 times the coefficients of x1, 1, 0. Okay, you see the coefficient of x1 for the first equation is 1, and the second is 0. x2 has the coefficients 2, minus 5, and x3 has minus 1, 3. And the right side is the vector b, you see. So by considering the vectors as columns of a matrix A1, A2, A3, and we have here the vector b, so it is corresponding to actually x1 times a1 plus x2 times a2 plus x3 times a3 is equal to b. And from here actually we have a matrix with columns a1, a2, a3 times the vector has the components x1, x2, x3 is equal to b. Okay, and shortly this one can be written as a times, which is corresponding to this one, times the vector x, states the variables of the linear system is equal to B. Okay. We have two options to state a linear system compactly. And you can see here, writing the entries of the vectors A1, A2, A3. So we get actually the coefficient matrix. This is the coefficient matrix, which is A1, A2, A3. Okay. This is the coefficient matrix A for the system. The coefficient matrix. So equation 3 has the form, as I said. Such an equation is called matrix equation to distinguish it from a vector equation such as shown in 2. Okay. This vector equation, as we can see, is equivalent to the matrix equation you see. Okay. Sometimes we will state the linear system as a vector equation. Sometimes we will state the linear system, as a matrix equation. And here we have an important theorem, as we can talk about. If A is an n by n matrix, okay, n by n matrix with columns A1, blah blah an, you know, the matrix equation A times x is equal to B has the same solution set as the vector equation, because you know they are equivalent to each other. In order to, if we want to solve this matrix equation, also we solve equally the vector equation, which in turn has the same solution set as the system of linear equations whose augmented matrix is this one. So this is corresponding to, you know, if you want to solve this system, so we have to find the echelon form of the augmented matrix, and we know the columns of the matrix A. This is the coefficient matrix, you know. So to write the augmented matrix of the system, first we write the coefficient matrix, and the last column is corresponding to the right side of the system, which is the vector B. And this is written in this form. And after solving this, by finding the echelon form of this matrix, so we find the solution, which means that actually we find the vector x here, okay, or we find the variables x1, x2, blah blah, xn, okay, is equal to b. They state the same thing, okay, they state the same thing. And the equation Ax is equal to B has a solution if and only if B is a linear combination of the columns of A, because, you know, as we can talk about here, Ax is equal to B is corresponding to the vector equation written here, which means that if we have a solution for the system, namely if you find the values of the variables x1, x2, blah blah, xn, so it also means that B is written as a linear combinations of the columns of the matrix A, you can see here. Therefore, if we find this answer, also we find the solution of the system, which is corresponding to this equality matrix equation. So we have a result here, which is stated as a theorem 4. Let A be an m by m matrix, then the following statements are logically equivalent. Namely, if you find one of them, also it means that we have the others also. In other words, for a particular A, either they are all true statements or they are all false. Okay, if you find, as I said, one of them, so actually we find the others written here. So for each B in Rm, you know, when we have generally a matrix equation. A is n by n matrix and x n by 1 matrix. So B will be n by 1 matrix, namely B has m components. It is a vector with m components. Therefore B is in Rm. So the equation has a solution. So if we have a solution for this system for each B in Rm, namely we take any arbitrary vector in Rm and we see that we have a solution for the system for each vector in Rm. So each vector in Rm is a linear combination of the columns of A, because it is corresponding to the linear combination of the columns which is equal to B, x1 a1 blah blah xn an. Okay, we have n columns here, and a1 a2 blah blah an have m components. Okay, m components. Therefore we will have m components for B, m components, and it is valid for every vector in Rm. Namely, when we take any arbitrary vector, let's say 1 0 blah blah -7, this is any arbitrary vector in Rm. Okay, we have m entries. You can write any numbers for the entries. So each B in Rm is a linear combination of the columns of A, and the columns of A span Rm. The columns of A span Rm, because for each B, for each vector in Rm, we write a linear combination. Okay, we write a linear combination. This equality is valid for all vectors in Rm. Therefore, Rm actually can be considered as a set spanned by the columns of the matrix A. Namely, we can write a code for Rm. We can state all the space just by knowing finitely many vectors, which is very, very interesting. A1, A2, blah blah, an. Okay, because each vector in Rm is a linear combination according to the definition of the set spanned by some vectors. So we have this equality. The space is the set spanned by these vectors written here. Okay, this is very interesting result, because just by using finitely many vectors, just by using the vectors a1 a2 blah blah an, so we can state all the space, we can find everything in the space just by knowing finitely many vectors. This is the key code of the space actually. And then we obtain A has a pivot position in every row. A has a pivot position in every row, because we have a solution for the system. To find the solution, we have to have pivot positions in every row. Okay, because if we don't have any pivot position for the last row, for example, sometimes we have 0 row and the right hand side is equal to some number which is not equal to 0, non-zero number like 5, if you remember, and we don't have any pivot position here, so we say there is no solution. But when we have a pivot position in this row like 1 or -1 and another number, so we can talk about a solution for the system. Therefore it concludes that we have a pivot position for the matrix A in every row. Okay, in every row. So after stating this theorem, let's see an example from here. Okay, another example. We have three linear equations: x1 plus 3x2 plus 4x3 is equal to b1 minus 4x1 plus 2x2 minus 6x3 is equal to b2 minus 3x1 minus 2x2 minus 7x3 is equal to b3. So for the given linear system, find the matrix equation. And the vector equation. Of the system. Vector equation. Okay. And for which values of b1, b2 and b3 is the system consistent? Okay, first let's find the matrix equation of the given system in the example. Namely, we will find AX is equal to B. So what is the coefficient matrix? So it is obtained by finding the coefficients of the variables respectively. The coefficients of x1 are 1, minus 4, minus 3, and the coefficients of x2 are 3, 2, minus 2, and we have 4, minus 6, minus 7 for x3, and x has the components x1, x2 and x3, and b has the entries b1, b2, b3. Therefore we have the matrix equation such that A is 3 by 3 matrix, you see, X is 3 by 1 and B is 3 by 1. So this is the matrix equation of the system. Namely, we can write this system as 1 minus 4 minus 3, 3, 2 minus 2, 4 minus 6 minus 7 times x1, x2 and x3 is equal to b1, b2, b3. Okay, 3 by 3, 3 by 1, by cancelling the common number 3, so you obtain 3 by 1, as you can see. And the vector equation easily also can be written in the form. So the first column has the entries 1, minus 4, minus 3. So this is written as also by applying the product of the matrix A and the vector X that we know now. So directly we write A1 x1 plus A2 x2 plus A3 x3 is equal to B. Okay, and A1 has the components minus 1, minus 4, no, minus 1, it is plus 1, sorry, plus 1, minus 4, minus 3, 3, 2, minus 2, 4, minus 6, minus 7. Sorry, you should write the vector equation. I am writing again the matrix equation. So you write like this one. A1 has the components 1, minus 4, minus 3 times x1 plus A2 has the entries 3, 2, minus 2, which is the second column of the coefficient matrix, as you can see, x2 plus 4 minus 6 minus 7 x3 is equal to the vector B, has the components b1, b2 and b3. So this is the vector equation, of the system, and this is the matrix equation, So for which values of b1, b2 and b3 is the system consistent? For this, of course, we should find the augmented matrix of the system. So first we should write, there is no space here, therefore I should open another page. So the augmented matrix of the system will be writing the coefficient matrix first, 1, minus 4, minus 3, 3, 2, minus 2, and 4, minus 6, minus 7, and the last column is the vector B, you know, B1, B2, B3. Okay, first we find the first pivot position, which is located in the first row. So the leftmost non-zero constant is 1, and it is in the first entry in the row. Therefore, we can say it is a pivot position for the first row. So we should get 0 for minus 4 and minus 3 easily. You know, R2 is replaced by R2 plus 4R1, and R3 is replaced by R3 plus 3R1. Therefore, we have 1, 3, 4 B1, and 0 for R2 for R1 for R1 12 plus 2 is 14, and 16 minus 6 is 10, and we have for B1 plus B2 for B2 plus 4B1, and 0 9 minus 2 is 7, and 12 minus 7 is 5 and B3 plus 3B1 for 3B1, right, 3B1, okay, 3B1. And then the second row operation will be, so after finding the second pivot position, so the leftmost non-zero number is 14, as you can see. Sorry, therefore we should get 0 for 7, so the row operation will be for the third row. We use again replacement. R3 is replaced by R3 plus minus 1 over 2 R2. 1 over 2 R2. So we have 1 0 0 3 14 0 4 10 4 10. So minus 1 over 2 times 10 is minus 5, plus 5 becomes 0, and B1 B2 plus 4B1, and minus 1 over 2 times R2, namely B3 plus 3B1 minus 1 over 2 times the second entry B2 plus 4B1. Okay, that's it. So you know the first column is corresponding to variable x1, the second one is x2, and the third one is x3, and we have the zero row for the coefficient matrix here, namely the coefficients of x1, x2 and x3 are 0, namely the left side of the linear equation becomes 0, and right side is equal to b3 plus 3b1 minus 2b1, okay, from here, minus b2 over 2, and from here we get b3 plus b1 is minus b2 over 2, okay. So in order to have at least one solution for all values of b1, b2, b3, so we should get this equation. So there exists, namely the system is consistent. We have at least one solution if b2 over 2 is equal to b1 plus b3, okay. b2 over 2 is equal to b1 plus b3, which means that we don't have a solution for all b in R cube. So just we can take the vector b in R cube satisfying this equality, like for example let's say b1 and b3 is 1, so b2 becomes 4. So we have a solution for the system if b has the components 1 for 1. But for another b, let's take for example Is there another b here? Don't satisfy this equality. 1 1 1, for example, 1 1 1. So when we write these values into the equation, so b1 is equal to 1, b3 is equal to 1, so 1 plus 1 is 2, and b2 should be equal to 4 according to this equality, but we have 1 here, so we cannot take this vector, which is a vector in R cube. Therefore, there is no solution for the system if b has the components 1 1 1. So we have a special space for b. Okay, this is a subset. This is a subspace of R cube. Okay, subset of R cube. Therefore, the columns of the matrix, do not span R cube, namely span A1, A2 and A3 is not equal to R cube, because this vector is not a linear combination of the columns of the matrix A, okay, of the matrix A, which is the coefficient matrix written here, you see. Because we don't have a solution for this vector, okay, we have impossible situation here when we write 1 1 1 for b3 b1 and b2, so we obtain a non-zero constant for the right hand side, which means we have impossible situation here. Therefore, b is not in the set spanned by the vectors a1, a2, a3, which means that this set does not cover all vectors in R cube, which means we have this inequality. And as you can see, we don't have a pivot position here. Therefore, the last part of the theorem is also not valid. Okay, you see, A has a pivot position in everywhere, but since we don't have a solution for B has the components 1 1 1, so we don't have this property. Also, we don't have this property, as you can see, and B is not a linear combination if it has the components 1 1 1, as you can see. Therefore, the first property is not satisfied. But we have a lot of vectors, infinitely many vectors for B, like 1 for 1. You can write any other numbers, 1 2. So B 1 2, B can be also 1 2. So this becomes 3 times 2 becomes 6. And you can increase examples for B satisfying the equality, which means we have at least one solution here. Okay, and that's it. Thank you very much for your listening.